was very happy to be called, and actually my first thought was to decline the invitation because, as many of you know, I've not been doing research for more than 5 years because I changed job. But when they told me that I was the right guy to talk about Marcello Boiatti's ideas, not just the works, I said that I could not refuse, and I'm very happy to be here. I was very happy to see Mark not online, but his video, and he said many of the things that I might also repeat during this seminar. And okay, the title is slightly different from what is written in the program because I put an and instead of s, because people might say that you have complex systems that are not living, and which is actually under debate because you always go back and forth between dualism and the merging of life, and people can say different things about that. But of course, you can imagine that a critical system, like for example, I don't know, a ferromagnet at the Curie temperature, is not really living, even if it displays some signs of complexity. And I want to thank everybody who is here, and I want to thank everybody that is online, especially if they are from the States, because I don't even know what time it is there, probably very, very early in the morning or late at night. Okay, this guy was Marcello Boiatti, and we have got to know him very well because in late 80s, early 90s, we used to make a lot of meeting, especially on Saturday, especially at the physics department, first at the mathematical department, then at the physics department. And he was always attending and was exchanging ideas with the community of mathematicians and physicists. And most of the work that I've been doing since then actually owes a lot to Marcello Boiatti. Sometimes I say that I learned more physics from Marcello Boiatti than from many of my physics teachers without, I don't want to offend anybody, but for sure it was up to date. And I translated into English the summary of this book that I think it was out in 1996, so if you contextualize, 1996 was an important moment for the rise of complexity because, the idea of explaining living beings with mathematics was old. Everybody remembers hacking and cybernetics and all this stuff. Still, there was still something missing, and the new discoveries on chaos theories and on fractals had revived this idea and actually made the complexity field raise again. And probably that was really a little revolution at that moment. I remember that, for example, in the Italian newspaper, Il Manifesto, there was a weekly insert that was called the Blue Orange, where you could read about complexity and chaos and fractals and things like that, something that, it's almost impossible to think about something like this in Italy now. You can imagine. Okay, so as you see, it talks about networks and the individual, so the idea of emergent properties, but not just, a lot of particles are able to make a cell, but the idea of networks. And then again, the idea of metabolic networks, so complex networks. At those times, we didn't have even the names to call them, small words, scale-free, and things like that. Still, it was already suggesting something like that. And then, of course, the theory of complexity, the idea of a long-range correlation that we were studying, in a sense, together, during those years. And the first thing that I want to say, this is the summary of the talk, but actually I will not go through everything because I will not have time. But I put everything because please interrupt me if there is something you want to know better than the other. I have much more material that I'm able to talk about. In fact, Marangoni told me, you have so many slides, but don't worry, I will not, I will not go through all of them. So one of the tenets, one of the things that we learned by Marcello Boiati, I learned by Marcello Boiati, but I think many people learned by Marcello Boiati, is the importance of multidisciplinarity. And multidisciplinarity that is not just a discipline that has something to give to another discipline, but the idea of developing a common language and to work together. So not just be able to analyze data, but to be able to know the data, to have an understanding of the data, to work together with the biologist, for example, or with the genetist, or things like that, okay? Or with the psychologist, if you want to. He adds, because it is not true that those people are not able to understand the mathematics. The most important is to make it simple. And I realized that, especially, and we have seen this in the last 2 days, when we discover something that is new, it's the first time that we get to a conclusion, and so sometimes it's not the easiest way to tell things. Then things become easier and easier the older they get, and they get to textbook and things like that, but then we lose our interest in them, so people do not talk about this stuff in conference. But now that I'm teaching in high school, I really want to press the scientist community to collaborate with people that has to teach easy mathematics to children, because the easy mathematics would make physics or science more interesting. Okay, and for example, physics might not be really interesting. Mathematics is always interesting per se, but physics sometimes, especially in high school, is boring because we do something that is very old. Okay. Oh, sorry. I have to say what I will be talking about. I will be talking about the first. Well, it was not the first work that I did as a scientist, but almost. And it was like 1995, 1996. Was complex in DNA evolution, and just as a way to show how multidisciplinarity worked at that time, and then I will also talk, like this is like a taxonomy, okay, from the cell, okay, to the brain, to language. Oh, actually, and then the origin of life should be in the middle, but this is more chronological in this, where I got to this stuff. The idea is that multidisciplinarity, it makes us able to tackle the difficult problems, like the hard problems of consciousness, okay? So something that really requires different layers of understanding, different levels of understanding, and you cannot do as a physicist or as a biologist or as a philosopher. You really need to harmonize all competencies in this case. And okay, let's go to DNA correlation. I will not be too technical. I will skip a lot because we have heard a lot of technical stuff. I have a lot of slides, so if you want, if you're interested maybe in the question, I will go through that. And okay, let's go. This is the first paper that we wrote that really were following the discussion with Marcello Boiati, yes. And what we noticed that the DNA could be analyzed with some in a way that it was possible to see that the long-range correlations were apparent. And so it was not by chance, and a few papers had appeared by Stanley's group in America saying that, you know, long-coding regions are there because of to keep the DNA together in the nucleus, and so they came out with a model that was the crumpled global structure, while the code in DNA was actually random because it had another function, and since the real alphabet was the alphabet of the protein, it was not easy for the code in DNA to carry long-range correlation. And what we found is that this is actually not true, but, and that was actually an idea of Maria Barbi. Well, probably the idea was mine, but she did the work. so she, but what I wanted to show is that it was apparent to us that, and that was actually related to what we have been talking last days, was not due to fractional Brownian motion, but you see that, however, it is distribution is distinguishable from a Levy process. We said that the DNA is a Levy process, a Levy flight, and which was controversial. So what we did was to run a map that we knew that would give rise to a Levy flight, and then we saw that the numbers of the excess of ones with respect to minus ones of the map was the same of the excess of purine with respect to pyrimidines. There are two kinds of nucleotides in the DNA length. And then, of course, this does not prove anything, but we were able to look at the distribution and to the scaling of the distribution. At those times, the diffusion entropy analysis was not yet invented, so what we were doing, we were just superimposing the distribution at different times, maybe smoothing them a little, and we saw that there was no difference in correlation between viral DNA, so essentially all coding, because it came from what diseases are three substrains of cytomegalovirus, and this is a non-coding part of human DNA. And we also see a kind of complexity matching. They say that the mu, now what is called the mu at that time, we call it Z, was roughly 5/3 both for the genome of a virus that was infecting the human and the human itself. Okay, is it a real complexity matching? Well, this is controversial because, of course, we are talking about the position of the nucleotides in a sequence, which is not a physical time. Okay, and the complexity matching is supposed to be a kind of fractal resonance, okay, that has to work in time. Still, I have to say that DNA has to open, has to go to ribosome, and these things happen in time, so we actually don't know. But the idea at that time was that DNA had to be a polymer that had to be very densely packed into the nucleus without any knots, because if it had knots, the enzymes could not reach some parts, okay? So you have to imagine to have a kind of chain, let's say a necklace with a lot of beads, and then you squash it, you just shrink it to a ball, and then you do it again, so you have another necklace with another order, and then you do again, and then what you get a densely packed structure, but without knots. And we were able, this work has been done with Buiatti, Marco Buiatti, the Marcello's son, and we modelize the crumpled global structure like a Calais 3, and we had this idea, okay, and this is already something that has probably something to do with what we have been discussing so far, because this DNA interface is like a sphere, or at least has no as a symmetry in the sense that it looks like the same if you rotate it. So the stationarity for sure is not with the reference of the position of the length. Is more with the reference of different circles. So what we did, we ran the map that we showed before on a spiral, so in a sense trying to mimic this kind of stationarity, and then we unwrapped that, and what we got, we got this stuff that we could see if it was fractional Brownian motion or Levy process, which was a problem because you see that this is the scaling of the Levy process, where beta is the long tail of the autocorrelation function, and this is the scaling of a Levy flight for the distribution of the excess of pyrimidines or purines in a window of length t, and this is the scaling relation. So actually, you could see the difference if one of these holds and the other does not. Unfortunately, in this case, alpha was, well, mu, okay, so was 2.5, which is exactly the only value where these two delta are equal. Okay, but okay, this is just the case, and oh, I didn't show. We didn't run the diffusion entropy, but we rescaled the DNA, and actually it looked like it was a fractional Brownian motion. Okay, which is interesting because we realized that if you have something that is more dynamical than a fractional Brownian motion, so it is a Levy flight, which is actually more dynamical than a fractional Brownian motion, you can get fractional Brownian motion if you introduce at all scales some kind of randomness. And this randomness is given by the fact that you crumple the nodes in this way, in this geometrical way. There is no randomness here, but this Calais tree introduces a disorder that makes the sequence indistinguishable from fractional Brownian motion that we know is not. And then later, since, and this ends what I have to do, what I have to say with DNA. And the second things I want to talk about had to do really with a new tenet of complexity, which is network, okay? And an exercise that I did, this is rough, everything is unpublished. Actually, the software was running in a CNR server for a while, was to, what has we had to do with that? Actually, he didn't work on that, but we discussed this stuff with him, and so my idea was to, when I was asked to join the Institute of Computational Linguistics, I thought it was easy for me to redo with language what I had done with DNA. Okay, but actually I discovered that we can do much more than that, because, for example, in language, you know what the semantics are of the words. Okay, then you have a lot of problems because the same word can have completely different meaning. For example, in Italian, stato can be a verb or a noun, a state or been, but also in English you have a lot of examples like this. And so what I realized that after a few attempts that I did not get anything, but yes, seeing that there were long-range correlation, but so what? What do you get with the long-range correlation for the, well, it was difficult to do it for full words, but you could do it with for letters, okay? If you run, at the time we had the diffusion entropy, if you run diffusion entropy with a letter on a text, you see long-range correlation, then so what? Nobody understands why, and actually somebody had seen it from the 60s, and nobody could understand why. So my approach was to think that the process of producing language is actually a complex process because it has to do with our brain. And in our brain, we never utter words alone, but we, at least the minimal phrase, is made by a noun and a verb. And this process is called predication, okay? And so actually the idea is that you have of all the words that you have roughly different kinds of words that refers to parts of speech. So the adjective, the articles, and whatever. But let us assume that most of the meaning is given by something that refers to objects that normally are nouns, and something that refers to actions or descriptions. That could be adjectives, adverbs, but mostly are verbs. There is no phrase without a verb. Okay, and so you can read automatically, you can make a computer read a long text, and you can extract pairs. Pairs where, for example, a noun, which is green, is the subject of a verb. Okay, for example, a dog eats. So you have the noun dog and a verb to eat. Okay, you found it, so you just put a link on your bipartite network. The attention that we did this stuff when Barabas's book was not over yet, was not out yet. We didn't even have the names to describe this stuff. So the idea was a really complex idea that semantically similar nouns had to be direct object of semantically similar verbs and vice versa, which from the point of view of logic is a paralogism. No? You are defining something with respect to something else and then go back, which from the point of view of normal science would be a nil-post problem, but actually complexity is better than that, and actually you can try to find what is called a bunch of nouns which have the same bunch of verbs, and this can be a sort of super pair. And you can run something like, this is a hidden Markov model, then you can do a straightforward expectation maximization. This has been done by others, does not work that well, but what works well is a physicist idea, for example, to run a random walk on this network and to find all the random walks that closes and give a rank to this random walk, and the rank is just the probability that that random walk happens. Okay? If you do like that, you face two problems. And one is that this is considered from the point of view of computer science an impossible problem. Okay? But actually what happens is that it closes. You run it, and in a couple of days, we had a couple of journals, so a lot of text, it ends, and that was surprising, actually not surprising, because something that is impossible to be done with a random graph is possible with a graph that is not random, is a scale-free graph. Then we didn't know anything about that at that time. And we discovered that, for example, the probability, okay, then I will skip out, we do all the stuff, but for example, the probability of a noun to be in an analogical proportion is in fact another network, and it is scale-free, And the ranking distribution, this is actually the ranking distribution for this kind of stuff, is an inverse power law. We see 1, 2, 3, 4 decades, and then it dirties a little bit for decades here, with index almost 1, near 1, okay? And this is important because we could also run a simulation with scale-free networks on this graph and to see the random walks, how it closes and how it ends. And we could find that you can get a weight in time distribution to come back to the first recurring time. And this weight in time distribution is an inverse power law. It is a renewal process, and it has an inverse power law distribution of waiting times. And we could relate this index here of the ranking distribution with the index of the waiting time distribution. And we did something more about that. So actually, these are proof that you have renewal process if you select the right words. I don't want to do that. But we did this also analytically with the Frobenius-Perron heuristics. We were able to compute the waiting time distribution in terms of the degree index. Okay, and this was also able to derive the Zipf's law, which is actually an empirical law about every language in the world that says that you utter a few, only few words many times, but most of the words are uttered one time or two times. And actually, you have a frequency rank distribution, which is just the frequency is 1 over the ranking, okay? And in fact, you could see that this was compatible. So if you do the probability of frequency, then you can run a central limit theorem, and then you find that you have a Levy process, and so you have an inverse power law distribution, and so you could rank the Levy utterance of words with the waiting time distribution that is a renewal process with the ranking distribution of the network. And that probably had also some interest in physiology because, for example, we made people write essays when they were doing simulation to the flight of Mars, and we saw that the index now is called the FA index, but I didn't do the FA, I just calculated the Zipf index because you need much less text. And you get a good R 0.6, 0.65, so it is an indication that it works. Then this one is probably something that if Grigolini is online, I should have talked about, but I don't have time. And so I will skip all this part that actually says that you can find this kind of network also in the brain if you analyze the cross correlation between EEG in different locations of your scalp. And actually we did something more because we saw that there is a difference between, this was the figure that Paolo talked about yesterday. But what is important is that we recovered everything that we knew. I don't want to do that, but for sure we saw, oh, no, I'm going back, I'm sorry. So, why is it that? We could also see that things go differently if you are awake or if you are asleep. So saying that you have a different kind of criticality when you are conscious and when you are unconscious. And the difference in criticality is that the system is still critical, so it's able to do branches, critical branches, but you have you keep some tenets of stational criticality, like the giant cluster when you are awake. So actually, you're not doing much computation in parallel, let's say. you have one thing at a time. You have consciousness. You have you are working serially, okay? While during sleep, your brain work as much as during wakefulness, but are doing many things in parallel, and you are not able to get a unity, okay? So this is what happens in sleep and in consciousness. Then the idea of this one was taken by people. Well, okay, I think that I think this is another experiment on perception. And then this one, I wanted to talk about that, is the origin of life with renewal process, but I think I don't have time to talk about that. So, well, okay, that's the end of the talk. And sorry if it was a little bit, a soup of many ingredients, and the soup did not end up quite well, but I think that you find something interesting in that, so I thank you. From online.
Well, I would like to make a question. Well, there are many questions that I would like to do, but since we have time very limited, I limit myself to make a question. You mentioned the fact that DNA should be described by a Levy process, but there are good reasons to believe that it might become an FBM process. This is, in my opinion, extremely important because one of the challenging issues that you are addressing also in this conference is yesterday we had Ioni and April talking about the mystery of biophotons that are at the very beginning characterized by crucial event and later had become fractional Brownian motion. And also experiment done on the brain of people under the influence of increasing pathology of increasing severity, that they move from a condition that is a Levy walk to FBM. I believe this is an extremely important issue that this paper that you are showing to us might help to settle. I would like to get your opinion about that.
Okay, in this paper, before going through this machinery here, we also made something very easy. And for example, we convoluted the Levy process with a Gaussian probability of initial condition. And we saw that from the point of view of analysis, this was indistinguishable from a fractional Brownian motion. I don't know if that has to do with biophotons, because it might be that when the plant grows, it might have different sites, or the mass is bigger, so maybe that you still may have renewal events, yeah, but you have different sources of renewals. So in a sense, they introduce kind of disorder. That is an easy speculation.
Yeah.
I'm not in that field, so I don't know.
Yes, yes. But I think that it's extremely important to understand if this is a process that, in the case of human beings, in the case of the brain, might be origin of pathology. It might be a way of understanding the emergence of a disease.
No, and I don't really understand how qualitative process, so or a dichotomous process like this, so counting process can give rise to a fractional Brownian motion. It doesn't seem dynamical to me, and we also proved them, with the four terms for some function. It is difficult to get a fractional Brownian motion. So the Levy process is probably the process I would bet into. So if you have fractional Brownian motion, you have to understand why, yes. So yes. There's some disorder. But I would say that dynamically, I would expect a LV process always. So when you have a counting process, something like
Yes.
that.
It would be nice for you to contribute to the last session where we are going to discuss this issue, because you have some results on this. Also, the work that was discussed yesterday by Marco Bianucci is connected to this issue, and it would be very nice to make a conclusion at the end of the conference.
Okay. They are making me glances that I have to end.
This is a very interesting discussion, but we have a few time to dedicate. Okay. Thank you again, Paolo.
Okay.
Now, thank you.